Right, now let's get on to Ampere's law. Unlike electric fields, magnetic fields don't originate from point charges, but they form a continuous field of loops. This is, in essence, the no monopole law. For example, if you cut a magnet in two, the north and south pole will remain the same in direction for both parts. So if you keep cutting a magnet, the orientation of the magnet will determine what its north and south pole is. So if you keep subdividing that magnet, but you don't alter the orientation of the magnet, the fields will remain the same. The field lines, the north and south pole, etc. Now, the no monopole law states that the magnetic flux over any closed surface is equal to zero. It follows by the magnetic field. It follows that the magnetic field must be divergence free. The magnetic circulation around a closed path is the line integral of the magnetic field around the path. The integral form of Ampere's law states that the magnetic circulation around a closed path C is equal to the total current I flowing through any open surface S and is bounded by C, multiplied by the permittivity of free space, which is given here in its equation. Now, the sense of positive progression around the orientation of C are linked by the right-hand grip rule. Ampere's law only applies to steady current distributions. Now, the curl of the magnetic field is a vector whose components are the magnetic circulation per unit area. In Cartesian coordinates, this is the curl acting upon a magnetic field B. Right, the curl theorem states that the line integral of a vector field around a closed path C is the surface integral of the curl of the field over any surface S that is bounded by C. So here we have in equation form. Now, this leads to the differential form of Ampere's. Curl of B equals the permittivity of free space by the current density, and it's valid for steady state distributions only. Now, I'll give an example below. Here's a cylinder. This cylinder here is a Gaussian surface. So it exists purely as a mathematical object, and the current carrying rod is here, and this is supposed to represent a physical and actual thing. Anyway, we calculate the magnetic field due to a steady current through flowing along an infinitely long cylindrical conductor of radius A, as shown here. We choose cylindrical coordinates system with z-axis pointing along this cylinder's axis in direction of the current. The most general field is given here. This has axial and translational symmetry of the cylinder, so it further reduces here as it's only dependent on the radial part. Right, because magnetic field can't depend on phi or z, and the Biot-Savart law implies that the magnetic field produced by a current element is perpendicular to the element. All the current elements point along the axis of the cylinder, so the magnetic field must be perpendicular to this axis. It's given here. Next, we consider a closed cylindrical surface S that is coaxial with the conductor. The magnetic flux through each end of S is zero because on each end ds is aligned with Ez, and br.ez equals zero. Therefore, the magnetic flux through S only depends on the flux through the curved surface. So here, where r prime and L are the radius and length of the surface. However, no monopole law requires total flux through S to be 0. So B of R prime equals 0 for any R prime, and L. So the magnetic field taken for B of R, so magnetic field taken for B of R, so magnetic field taken the form of circular loops along the axis of symmetry. I think I wrote this twice here, I've confused myself. To apply integral amperes, we must choose a path through C bounding on an open surface S and exploiting symmetry. We choose C to be a circle of radius r greater than a, centered on a and perpendicular to the cylinder, given here. The corresponding open surface S is the area that has C as its perimeter. The unit normal to the area is taken to be the direction of increasing Z. The right-hand grip rule shows the sense of positive progression around C as the direction E phi is in the direction E phi. It follows that the integral magnetic field around C is given here. And the current flowing through the surface S is just the current carried by a conductor. So Ampere's law gives this, and solving for B phi of R gives this. Right. For Ampere's law inside a cylinder, it's as before, but our Gaussian is here now on the inside. The direction of current sorry. The direction of current flow is parallel to EZ, and current density in a conductor is found by dividing the total current by the cross-sectional area given here. To find a field inside the conductor, we choose a closed circular path C, as in the case for the outside, but this time with the radius within the cylinder itself. Now, the magnetic field is parallel to dl equals r d phi e phi at all points along C, so the line integral around C is given as such. Now, the total current passing through S is here. For R less than or equal to A, as the current density is uniform, this is equal to the total current multiplied by the fraction of the cross-sectional area of conductor covered by S. So Ampere's law gives this. So inside the cylinder we have this. Now differential Ampere's law. Using same coordinates and symmetry arguments here, but now with curl of B equals the permittivity of free space by the current multiplied by the current density. In this case, current density is the current divided by the area along the EZ. And so for R less than or equal to A and 0 otherwise, curl of B equals this, where F0 for R greater than A and this otherwise. So rearranging, we get our RF, and the PDE can be integrated to give this here, and where F equals the permittivity and the current density, and well, we're going through the calculation quite straightforward to follow. We have the integrals of the constants of integration, and the magnetic field should be finite at R equals 0, so the constant G is less than or equal to A, and therefore we get this here for R is less than or equal to A. Now solving for R is greater than A with F equals 0, we come to this, and solution at R equals A gives this. Therefore the solution is given here, and this is the differential Ampere's law. Thank you.